Hello everyone, welcome by the first answer video of this MOOC. Every week we will explain how to do the exercises so that you can learn from it and do it the correct way at the graded questions. I will show you how to do the exercise about the tubular reactor and to make a concentration profile over this reactor. At the left top I've drawn this reactor. And in this reactor we have a reaction from A to product B that is also getting us 2 of C, a byproduct. And to make this profile, we're going to have to take a look at the sketch. And I've taken a little slice over x plus dx, so the difference, the width of this slice is dx. And we always do this when making a profile. It's called a micro balance that we are going to use. Over this reactor that has a diameter of d, and flow is going into these little volume we have there, and in this volume we also have a reaction. The concentration in this V will be other than in this V. So we are going to use the mass balance here, since you want a concentration profile, which is in minus out plus production. Just the normal mass balance. And it is steady state, so this is 0. In is just the VV times CA at x. Out is the same flow, but another concentration, because it is CA at x plus dx. And the reaction is minus Kr times Ca times A times dx. And actually this is the volume. Only already split out in area and the width of the slice. So I can rewrite this to this equation, and you can see later why I am doing this. Minus Kr times Ca, without the minus, times dx. And now I can rewrite this to a differential form, and you have to watch out to use the correct minus sign. And you should always check this when you are doing these kind of calculations. And I can rewrite this to a more common form, which is the differential equation. Right, so we recognize this. And we can solve this by separation of variables. I can show you quickly how to do this, but I'm sure you're already quite familiar with this if you have followed the first MOOC. So integrate this, and you will get the ln function of Ca times is equal to the right side times x, and never forget the constant. You can rewrite this. Don't forget, your constant also changes because you are doing a mathematical conversion of it. With the initial condition of Ca at x is 0 is Ca 0, and I can always later on fill in a number here. This is more easy if you want to tune with, for example, this initial condition. And if I fill this in, you can see my final equation. So this is the concentration profile of Ca over reactor in x. So I can now determine the concentration of A in the whole reactor. The next question was to sketch a graph of all the components inside the reactor. And we could already draw Ca, right? We know how it's made. So it's a negative exponential equation. Now I want to know how to draw this concentration of B, and I can do this all over again and doing this balance thing, but I can also think logically and think, what is the concentration of B? Well, this is at x is 0, this should be CB0, right? And then for every a molecule conversed, I can get 1 back. So this Ca0 minus at that point Cax, so the amount that is conversed from A is actually conversed into B, so a plus sign there. And the same counts for C. There, the C0 plus this term, only it was 2 times, so times 2. And also CB0 was 0 and CC0 was also 0, so this is what we are left with. And I can also draw this, right? Because I know that B starts at 0 concentration, and for every molecule A conversed, we get 1 of B back, and we get 2 back from C. So this is the graph that you should have drawn. Now the question was that how long the reactor should be for the concentration of C not to exceed 11 kilograms per cubic meter, since that would poison the catalyst. So now I want to make a profile for C. And I'm going to use this. I'm not going to start all over, since we have this term, and I can rewrite this equation into this, and this is Ca0 minus a half times Ccx, and I can just put this into this equation, and that would eliminate Cax, right? And the only variable left would be Ccx, and if I do this and I rearrange some things, I am left with this equation. And as you can see, it is the same equation as I have drawn in the left graph, so that was correct. And now I only have to fill in all the variables, 11 kilograms per cubic meter for this. All these set variables are known, and it gives me 50.9 meters of tubular reactor. So this is the maximum. It could be less if you want to. Thank you for watching this video. If you have any questions, please feel free to ask on the forum, and I'm sure your peer students or we are happy to answer them.